Hi again. In this chapter, chapter 5, we'll look at hypothesis testing for the model we looked at last chapter, the bivariate regression model. We'll look at confidence intervals, and we'll look at something called the Gauss-Markov theorem towards the end of the chapter, which will involve this concept of homoscedasticity and heteroscedasticity I mentioned in the last video. So let's get to testing hypotheses in the one regressor case. So testing hypothesis. Remember, our model is, let me move this down a little bit so you can see it, yi is beta 0 plus beta 1 xi plus ui. So that's our basic two-variable regression model. And we're interested in testing hypotheses about beta 0 and beta 1, mostly beta 1. Sometimes we'll be interested in beta 0, but for the most part, it's beta 1 that we're interested. For example, in the class size example, is the slope is beta 1, statistically significant? That is it statistically significant that when class size goes up, test scores go down? Or is that an insignificant result, or we really can't say there's a relationship there at all? So we can formalize that. Let's start off with a two-sided test for beta 1 hat. So in the class size example, what we want to know, our null hypothesis is that beta 1 is equal to, and the book uses beta 1 comma 0 as the hypothesized value, and that's going to be 0. So in general, our null is beta 1 equals beta 1, 0. This could be 1, it could be 3.7, it could be anything. In this particular case, we want to know if beta 1 is 0 versus the null that beta 1, the alternative, sorry, the null is h0, the alternative is h1, that beta 1 does not equal some value beta 1, 0, which in this case is 0. So the null is usually the standard knowledge, and what we're going to do is the null is going to be true unless there's overwhelming evidence to the contrary. So you find something you want to test and say, okay, in this case I'm going to say my null is that there's no relationship between class size and test scores, and I'm not going to reject that null unless there's overwhelming evidence to the contrary. And we'll see what overwhelming evidence means in a moment. Okay, to do these tests, there's a series of steps that you always go through. So what are the steps for this two-sided test? So the first step is to find, and the computer package will usually do this for you, it always will, find the standard error of beta 1 hat. The book often says SE of beta 1 hat. That's another way to write that is sigma of beta 1 hat. The estimated standard error is sigma hat of beta 1 hat. So we first have to estimate the standard error of beta 1 hat. So we need an estimate of that. Once we have that, well, in this case, the standard error of beta 1 hat in the two-variable case is the square root of sigma hat squared beta 1 hat, and sigma hat squared for beta 1 hat. This is the variance of the estimator beta 1 hat is 1 over n. We gave this formula in terms of expected values in the last video, in the last chapter. Now we're going to write the actual formula. It's 1 over n minus 2 times the sum from I equals 1 to n of the xi minus x bar times ui divided by the 1 over n times the sum from I equals 1 to n of the xi minus x bar. And then we want that whole thing squared. And if you look at the last chapter, what we wrote down, we wrote this as the expected value, or the covariance of x and u, and this is the variance of x squared. And these are the sample counterparts. This is how you'd actually measure it in the data. And so the first step is just to find this standard error. You're gonna have estimated u's. Sorry, these should be u hats. That's the estimated value of u. You're gonna know your x's. That's just data. You know what n is, so you can calculate this from your data and from the estimated error. And again, the computer will do this for you. Once you have that, the second step is to find the t statistic. And if you recall what the t is, I've written some of these down already. T is beta 1 hat minus beta 1 0 over the standard error, which we just wrote down, of beta 1 hat. This is the actual, and this is the hypothesized. So this is the actual estimate. This is the hypothesized value, and this is the standard error of regression. Now, the way it works, of course, is if these are close together, if our estimate is close to what we hypothesized, we're going to say, okay, that the null is probably true. We said the null was that it was 0. If those two things are close together, that's probably true. Because remember, beta 1 hat varies with the sample, so there's going to be some normal variation of beta 1 hat. We're not going to get the hypothesized value exactly, even if that's the true population parameter because of the sampling variability. But as long as this is close enough, we're going to say, yeah, we're probably right about our hypothesis. Well, what is close enough? When we do that, I like to write it this way. T is beta 1 hat minus beta 1 0 over sigma of beta 1 hat. This is just the standard error. So what we want to do is what I talked about earlier in another video was when we're going to reject this is when we get a certain number of standard deviations away. So this is the standard error that we sort of expect in beta 1. In essence, if this is more than twice this, turns out the right number is 1.96. But if this is more than twice this, then we're going to say that's too far away. The null is probably not true. We're going to go ahead and favor the alternative. But if these are very close together, if it's within 2 standard deviations, which is sort of a normal range, then we're going to say, no, we're not going to reject the null. That's close enough. So you find this t. Well, how do you know what's close enough or what's not close enough? Well, that's where the third step comes in, where you find p-values. There's another way to do this that you might have seen, but suppose we get a t equal to, I just made up an example here, 1.84. We're going to use the normal approximation, so we're not using the t distribution, we're using the normal distribution. If you look on page 758, you can find the probability associated with that t. So if you look that up, you'll see a number of 0.9671. So if you look that t statistic up in the back of the book, you'll see that the probability for that is 0.9671. What that is, that's a cumulative probability. So you've got a normal 0, 1. The t is distributed normal 0, 1. And so this is a normal distribution. It's centered on B1, 0, which in our case is 0. And this number that we've looked up, 1.84, that 0.9671 is the area to the left of that. So what that means is the area here is equal to 0.0329. Now we're doing a two-tailed test. And so if we were to do a two-tailed test, we'd have 0.0329 in there. And so our p-value in this case would be equal to 0.0658. If we do a 5% level of significance, remember how that works? Then since 0.0658 is greater than 0.05, that is 5%, you would fail to reject. So the null you would fail to reject in this case. Now, I actually prefer to do these a little bit different way, and that's the next way, actually, to do a t-test. So what you actually do, the fourth way, is to do the t-test. In this case, it's actually a normal test, what some books call a z-test, but that's okay. What you find in that case, this is a normal 0, 1. You find the t so that you have 0.025 in each tail. This number is 1.96, and this number is minus 1.96. So what we're going to say is if the t is somewhere in this range, in between the two, that's the fail to reject. We're not far enough away from the hypothesized value to reject. But if we end up in either one of these tails, then we're going to reject. So what you look at is whether the absolute value of your t is less than 1.96, then you fail to reject. So in our case, since t is 1.84, we're in here somewhere. We fail to reject the null. Now let me make this more concrete by doing an actual example. So remember that the test score example. The way you often see regressions reported is the following. So if you look in most journal articles in economics, you'll see something like this. The book uses STR here. I've been writing size. STR is student-teacher ratio. R squared is 0.051. And the standard error of the regression was 18.6. In parentheses, what they put are the standard errors. So this is the standard error of beta naught. And this is the standard error of beta 1 hat, beta naught hat. So this is SE of beta naught hat. Oops, I didn't write it. This is 0.52. So that's the standard error of beta 1. 10.4 is the standard error of beta 0. Now we want to test the null. This is beta 1 here. That beta 1 is equal to 0 versus the alternative that beta 1 is not equal to 0. So we form our t statistic. T is actual minus 2.28 minus hypothesized 0 over the standard error 0.52, and that turns out to be minus 4.38. So when we look at our t-test here, remember this t is distributed as a normal 0, 1. So this has a normal 0, 1 distribution, which we could prove fairly easily, and you should have in your last class. So our limits are 1.96 and minus 1.96. In this case, we're way out here in the tail at minus 4.38. So the fail to reject is between those. The rejection region is out there. So in this case, we reject the null. We reject that that beta 1 is 0. We reject that this is not anything different from 0. So we have a statistically significant relationship. And in fact, It's highly significant. It's way far away from the rejection point. If you were to go back to the T or the Z table, the normal tables in the back of the book, and look up the p-value for this minus 4.38, what we were trying to do before, this is so big that you won't even find it on the tables. It's just too far. But the p-value for this would be approximately 0.00001 for 4.38. That's the probability if I put 4.38 here, that's the area in both of those tails outside of that region to the right and to the left of it is only that amount. Since that's less than 0.05, we would reject. I think just doing the t-test is the easiest way to do this, but sometimes they're reported this way. Sometimes when you see a regression line, y hat is 8.7 minus plus 2.6 times x, they'll actually put the p-values in here, 0.02, 0.08. If these are p-values rather than standard errors, and they have to tell you in the text of the table, then we would fail to reject this one because 0.08 is bigger than 0.5, and we would fail to reject that this was equal to 0, and we would reject that this one. But most of the time, they don't put the p-values in there. They put the standard errors. That's the standard. So you just take your regression output. When you get it off of a computer, usually what you'll have is a table. It'll have like beta 1 hat, beta 2 hat, and then it'll have the value 698.9, is that right? Beta 0, beta 1, minus 2.28, and then it'll have the standard errors right beside it, 10.4 and 0.52. And sometimes they'll give you the t-stat and the p-value automatically. So it would actually have whatever those are. So you can just take your output that you get off the computer, look at this t-statistic and say, is the absolute value of that bigger or less than 1.96? And if it's bigger, then you'd reject. And so the computer usually makes this fairly simple. One-sided test. Sometimes what we're interested in is just a one-sided test. So the null might be beta 1 equals beta 1, 0. Maybe this is 0. Doesn't matter. This is just some number this is our hypothesized value. Versus, say, H1, that beta 1 is less than beta 1, 0. So what we have in this case is rather than a two-tailed test, we have a one-tailed test. And when would we want to reject the null? We wouldn't want to reject the null unless beta 1 is a big negative number. And so what we would do for a one-tailed test, with a two-tailed test, a 5% level of significance, we put 0.025 in both tails because we want the total to be 5%, 0.05. That's the rejection region. We want the rejection region to be a 5% region. If we do a 5% level of significance in a one-tailed test, then we're going to put 5% into here. Before, this was 0.025 because we were sharing it. So you wouldn't want to reject unless you had an overwhelmingly negative value for beta 1. Well, how negative should it be? Well, we just do the t is beta 1 minus beta 1, 0 over the standard error of beta 1 hat, beta 1 hat. that has a normal 0, 1, so this is 0. And if this is a big negative number, we're going to want to reject. In this case, instead of 1.96, the value that you get is minus 1.64. And so when we did this, our t was equal to minus 4.38. That's still way outside the rejection region. So we would reject the null that beta 1 was 0 in favor that it was less than 0 for the test we just did, because minus 4.38 is way out here in the rejection region. If we had gotten a t of minus 1.5, then we would fail to reject that it was 0. So you can do one-sided tests and two-sided tests, and the only difference is the value of the limit here. See, in the two-tailed test, what we're saying is we're going to reject the hypothesis. Here's 0. Our null is that there's no difference between these. Our null is that we're close to 0. This is beta 1 hat minus beta 1 0 over the standard error of beta 1 hat. If the null's true, we're at 0. If they're exactly equal, we're at 0. And we would never reject in that case because the estimated value would be exactly equal to the hypothesized value. Yeah, okay, it looks like it's darn true. When we're going to reject with a two-tailed test is if we get too big of, if beta 1 hat gets too big relative to this. In fact, if the difference is greater than 1.96 once we normalize, or if the difference is minus 1.96. So for a two-tailed test, the rejection region is two sides. And we put 0.025 into each tail so that the rejection region is 5% or 0.05. With a one-tailed test, we fold all this area over here and we get a different limit. But we're just, when we're rejecting is when we're too far away from the null and we reject in favor of the alternative. This one is this case. Now you can also do a one-sided test the other way. Let's go back to the one-tailed. But this time let's do H1, and let's just do it generally, is that beta 1 is greater than beta 1, 0. When we reject in that case? Well, again, here's the distribution of the t statistic. If they're exactly equal, we're not going to reject. If we get a big negative number, the alternative doesn't look like it's true, because this says it's positive. So we're not going to reject in this case. And again, this number will be 1.64. That'll put 0.05 into here. We're not going to reject in this case unless the t gets to be greater than 1.64. Unless the difference between beta 1 hat minus the hypothesized value over the standard error of beta 1 hat, which is the t has this distribution. If this is smaller than this doesn't look like the alternative's true, right? Because the alternative is it's bigger. So if we're way out here in this tail, we're not going to reject this in favor of this. The only time we're going to reject is if beta 1 hat gets bigger, enough bigger than beta 1 that it looks like this hypothesis isn't true. So our rejection region is out here. Okay. So that's all there is really to hypothesis tests for beta 1. What about testing hypotheses about the intercept, beta 0? It's the same. There's no difference. You just, now the null is that beta 0 equals beta 0, 0, 1. Beta 0, 0, the way the book writes it. And H1 is that beta 0 does not equal, this is a two-sided, beta 0, 0. So that'd be a two-tailed. So again, it's just, you find t is beta naught hat minus beta 0, 0, estimated minus hypothesized over the standard error of beta naught hat. And you get that from your computer printout. You find the t, and if the t is, for the two-tailed, minus 1.96 and 1.96. If you're out here in the rejection region, then you reject. If you're not, you don't. For a one-tailed test, it's just like we did before. So There's no difference here except we're just changing zeros to ones. And so conceptually, there's just nothing at all different here from there is from testing beta 1 hat, so there's no reason to go through this in any detail. Cool. Okay. Now let's do confidence intervals. Confidence intervals for a regression coefficient. The coefficients are beta naught and beta 1. I don't know if you can read that or not. I'm above. I put lines on the board to try to figure out where the camera ends, and I don't know. It's a little bigger than what I see there on the monitor, but sorry, but what it says is confidence intervals for a regression coefficient. Often we don't want to hypothesize a precise value. What we want to know is what are the reasonable ranges that one of the coefficients could take. So what values are most likely? And for that, we're going to use a confidence interval. So for beta 1, and it'll be the same for beta 0, there's two defs. There's two equivalent definitions. I like the second better than the first. The first is it's the set of values that cannot be rejected. So it's all the hypothesized values that would not be rejected by a t-test. And you can do one-sided confidence intervals, but you almost never do. Using a two-tailed test with usually 5% significance. You could change this. Sometimes people use 1% or 10%, but 5% level of significance is by far the most general, and it's what the book uses almost exclusively. Mostly when people talk about confidence intervals, these are equivalent definitions, but they have the following in mind. It's the interval that has a 95% probability of containing the true value. Of beta 1. So if we were to do this 100 times, draw 100 samples, estimate a regression 100 times, we would expect that 95 of those, if we did the confidence interval, the true value of beta 1 would be in there. It wouldn't necessarily, if you kept doing it over and over and over, on average you get 95%. So it's a range in which 95% of the time the true value will be in there. See, we're estimating beta 1 with beta 1 hat, and we don't know what the true value is. So we're going to put this range for beta 1 hat. This range, because it's a 5% level of significance, 95% of the time the true value will be in there. Now it's pretty easy to do this. What you do, and we could derive this from the t. Do I actually do that? I don't think I did. There's no need to do it. I think I might have done that in a later chapter, but we could actually derive this. But the t statistic will reject beta 1, 0, reject the null whenever the hypothesized value, beta 1, 0, is outside the range beta 1 hat plus or minus 1.96. This is 95%. Times the standard error of beta 1 hat. So the confidence interval is this range. It's beta 1 hat minus 1.96 times the standard error, comma, beta 1 hat plus 1.96 times the standard error of beta 1 hat. And I'm going to assume you did confidence intervals for in the statistics class you took, the prereq for this, and so you're familiar with this. You've actually derived these from t-statistics and the like. But that's the simple formula that we're going to exploit. For beta 0, it's exactly the same, except for beta 0, it'd be beta 0 hat minus 1.96 times the standard error of beta 0 hat, comma, beta 0 hat plus 1.96 times the standard error of beta 0 hat. So that's the 95% confidence interval. That's the range that 95% of the time the true value will be in. In the test score example, beta 1 hat was minus 2.28. The standard error of beta 1 hat was 0.52. So the confidence interval is minus 2.28 plus or minus 1.96 times 0.52. So what that tells you is minus, the confidence interval is minus 3.30 minus 1.26. That's a 95% because we use 1.96 here, confidence interval. So 95% of the time, if we draw a sample and calculate beta 1 hat, find its standard error, find this interval, 95%, the true population value, the actual true value of beta 1 will be in this range. So that's the 95% confidence interval or a reasonable range that you could expect for beta 1 to be within. Now, you can also do the hypothesis testing this way. Note that the confidence interval does not contain 0. So we would reject the null that beta 1 is equal to 0 because it's not in the 95% confidence interval. We'd reject that it's minus 1. We'd reject that it's minus 4. Anything that's not in this range, if we were to do a t-test, it would be rejected. So again, this is the range of things that aren't rejected. If I do the hypothesis that beta 1 is minus 1, I wouldn't reject it. If I did the hypothesis it's minus 2, I wouldn't reject it. So these are all the beta 1 zeros. That's that first definition of the confidence interval that would not be rejected. And again, another interpretation is that 95% of the time the true value is in that range. Oops, I lost my mark. You can also do a confidence interval for the predicted effect of changing x. That's probably a little confusing. Let me just do an example. Remember that yi is beta naught plus beta 1 xi plus ui. The change in y due to a change in x, delta yi is beta 1 times the change in xi. So if I want to predict, suppose I change class size by 2. We did that earlier. Suppose that this is class size and it's 2, and we change it by 2, we multiply by the coefficient. The predicted change in y would be minus 4.58. We would expect, if class sizes go up by 2, we would expect test scores to go down by minus 4.58. We can put a confidence interval around this. So the confidence interval for this, the confidence interval is beta 1 hat minus 1.96 times the standard error of beta 1 hat times the change in x, and beta 1 hat plus 1.96 times the standard error of beta 1 hat times the change in x. We'll do an example of this in a second. So let's do the class size example. For the class size example, beta 1 hat is minus 2.28. The standard error of beta 1 hat is 0.52. What if class size, which way do I want to go, goes down by 2? So that means that the change in x is minus 2. Well, this will be what? Minus 2.28 minus 1.96 times 0.52 times minus 2. That's the left interval. So it's just the confidence interval times the change, the confidence interval we did earlier. And the other one will be minus 2.28 plus 1.96 times 0.52 times minus 2. That turns out to be minus 6.60 and minus 2.52. So for a change in class size of 2, 95% of the time the true change in y would lie within that range. By the way, that's just taking, if I already had the confidence interval from before, remember what it was? For the test score example, it was minus 3.30 and minus 1.26. That's the stuff inside here. If I just multiply these by the change by minus 2, I'll get those values. I'm sorry. These should be positives because I let the class size go down by 2. So I multiply this basically by minus 2. If the class size go down, the test scores go up. So this is the 95% confidence interval for a decline in class size of 2. What I wrote down initially was for an increase in class size of 2. But again, it's just these things times minus 2. If it was for 3, this would be minus, if it went up by 3, this would be minus 9.90, and this would be, I don't know, 8 carry 1, 7, 4.78. 3.78. Sorry. So you just multiply the confidence interval by the change in x to get the 95% confidence intervals for those. So that's hypothesis testing and confidence intervals. Again, this doesn't contain 0, and so it's statistically significant. I'm not sure why the book threw the next section into this chapter. Maybe the chapter wasn't long enough or something. I don't know. We're going to come back to this topic again, but I'm going to stick with the book and just do what they do. But this is a little bit out of place given what we've been doing. But that's okay. We can handle it. And then we'll go on to hetero and homoscedasticity after this. So this is a section about regression when X is a binary, or sometimes it's called a dummy variable. So this is when X can only take on 2 values, and they're almost always 0, 1. So for instance, we might have a gender variable. So X is equal to 1, xi is equal to 1 if the person is a female, and 0 if the person is a male. So we want to have something like that. It could be, you could have a class size variable where X is 1 if class size is bigger than 20, 0 if it's less than 20, or it could be color. 1 if it's blue, 0 if it's not blue. Any sort of indicator like that. So you can take these binary classifications, and we'll learn later, you could have 3 colors, green, blue. You could have 2 colors, and then you can just have a couple of different variables, and we'll learn how to do that later. But for now, we just have a single binary variable because we don't have multivariate regression yet. So I can't have more than one category. But we'll see how to generalize this later. That's why I would have been tempted to wait. But these are called indicator variables or dummy variables. And the interpretation of the mechanics of estimation and hypothesis testing are exactly the same. But the interpretation is a little bit different. This is equivalent to doing a difference in means test, as we'll see in a second. So what we'll end up doing is testing for a difference in means. Let's do it. Let's do the class size example. So let's usually these are called dummy variables, so we use a di. So let's set di equal 1 if class size is less than 20, and 0 if class size is greater than or equal to 20. So we're going to define this variable di that looks like this. Now this is not so now we're going to write a model that says yi is beta 0 plus beta 1 times di plus ui. But we said the difference there is interpretation. This is no longer interpreted as a change in the slope because this is not a continuous variable anymore. It can only take 2 values. We write down a slope, xi and yi. Xi can take anything and you have this nice slope. That's not what's going on here. We'll see what's going on in a second, but basically what you're going to have is 2 different horizontal lines where one will have an intercept of beta 0 and one will have an intercept of beta 0 plus beta 1. And that you can test where there's a difference between these 2 things by testing whether beta 1 is significant. So that's where we're headed. Now, let me try to unpack what I just said a little bit more. So let's get rid of all the clutter here, and let me write the model again. So we have yi is beta 0 plus beta 1 di plus ui. And again, this is 1 if class size for district I is less than 20, 0 otherwise. That is greater than or equal to 20. So when class size is less than 20, when di equals 0, yi is beta 0. When di equals 1, yi equals beta 0 plus beta 1. Because when this is 0, we just get beta 0. When it's 1, we get beta 0 plus beta 1. So the expected value of yi given di equals 0 equals beta 0. And the expected value of yi given di equals 1 is beta 0 plus beta 1. So this is the population mean for a class size less than 20. That's the expected test score when the class size is less than 20. And this is the population mean for class size greater than or equal to 20. So we, in essence, have a model where yi is either equal to beta 0 or beta 0 plus beta 1. This is for less than 20, and this is greater than or equal to 20. And what we want to know is there a statistically significant difference between these two groups, between the group with smaller class sizes and the group with larger class sizes? And the way we can test that is by beta 1. So if beta 1 is statistically significant, this is basically y bar equals y bar equals. So you've got two different hypothesized means. So if beta 1 hat statistically significant, it implies a difference in the population means for the two groups. If beta 1 hat is not statistically significant, if we fail to reject, then we would conclude that the means for these two groups are the same. That it doesn't matter for test scores whether you're in the lower group or the higher group. All right. So to estimate this model, yi is beta 0 plus beta 1 di plus ui, you just treat this like xi. All the same formula for beta 1 hat works, same formula for t's work, same formula for confidence intervals work. There's nothing new here. So the null that beta 1 equals 0 versus the alternative, the two-sided, you could do a one-sided too, but we'll do a 2, that it's not equal 0. The t will be beta 1 hat minus 0 over the standard error of beta 1 hat. And you compare that to 1.96. And the confidence interval is beta 1 hat plus or minus 1.96 times the standard error of beta 1 hat. So you can either do a t-test and see if it's greater or less than 1.96, an absolute value, and reject or not according to that, or you can do a confidence interval and see if 0's in your confidence interval and do the test that way. Now in the book, they run this for the class size example. So for the class size example, if you define D that way, in Excel you can actually do if statements. So you could have a whole bunch, you could have all the class sizes. Then the next column could be if this value is less than 20, make this a 1. If it's greater than or equal to 20, make it a 0. And you could write that if statement in Excel and then create this new value and use that to run a regression. If you did that with the test score data, test score class size data, you get test score equals 650.0 plus 0.74 times d, score I, di. R squared is for this model is 0.037. The standard error of regression is 18.7. I should have, let me move those. Sorry. R squared is 0.037, pretty low. Standard error of regression is 18.7. That's big. We still don't have a very good fit at all. Shouldn't surprise us. The standard errors are 1.3, and this is 7.4, not 0.7 or 7.4, and this is 1.8. A quick way to do a t-test, you really should use 1.96. If I do 2 times this, I get 3.6. It's less than this, so we're going to reject. We'll see that in a second. Okay, so our null is that beta 1 equals 0. The alternative is that beta 1 does not equal 0. And again, this is there any difference in the population means, is the test, between the size less than 20 and size greater than 20. When d equals 0, score hat, the average test score is 650. When d equals 1, the predicted test score, the average across these districts, it's just this plus this times 1. The first case, it's this plus this times 0. It's going to be 657.4. So those are the predicted means. Is that a statistically significant difference? Well, if we do the t, it's 7.4 minus 0 over 1.8, which is 4.04. That's a lot bigger than 1.96. And so they're significantly different. We reject the null. So there's a statistically significant difference between the population means for these two groups. What about the 95% confidence interval? For beta 1, it's going to be 7.4 plus or minus 1.96 times the standard error, 1.8. So the confidence interval is going to be 3.9, 10.9. 0 is not in there, so we reject the null. But 95% of the time, the true value is going to lie within that range. And so with binary variables, there's nothing really different except the interpretation of what the coefficient beta 1 means. It's no longer a slope. What it represents is the difference in the two population means for the two groups defined by di. Okay, let's move on. Let's see if I have enough time to finish this on one video. I think so. We're going to run a little bit over an hour, maybe a little more than a little bit, but I don't think it's enough to break up into 2 videos. So let's look at next at heteroscedasticity versus homoscedasticity. Different variance versus same variance. And when we're saying that, we're talking about the error term. Now this is not for the DI model, the XI model. We're actually back to the standard model. So our model, let's go back to the model. yi is beta 0 plus beta 1 xi plus ui. And remember that we said, here's xi and yi. We have some true, this is the true regression model, not the estimated. This is the true population regression model. We looked at this before. We said, well, one assumption that we make, this was assumption 1, was that conditional on xi, the distribution of errors has a 0 mean. I've made it look like it's normally distributed, but I didn't quite hit it right. The peak should go right through there. And no matter if it's homoscedastic, the variance of, this is the variance of the ui terms. So what this is this is sigma squared at xi. This is sigma squared ui. So that's the spread of this distribution is the variance of ui, whatever ui means. Out here there's another x, xj. And we could write down its distribution of its errors. And I meant for these two things to be identical, look identical. This would be, the variance here is going to be sigma squared uj, because we're at the xj. If those two things are the same, if sigma squared ui equals sigma squared uj for all I and j, no matter where we're at, if every one of these is identical, that's homoscedastic. And when we have homoscedasticity, a lot of the formulas we've been looking at are going to simplify quite a bit, and we'll show that in a second. And it'll also give us some additional properties about the OLS estimator that are nice. And when it's homoscedastic, the estimators of beta naught and beta 1, beta naught hat and beta 1 hat, are going to be the very best you can do with a linear estimator. You can't do any better than that no matter what. And so it'll have some very nice properties. Often, though, especially in economics, what will happen is these errors will not have the same distribution. In that case that I just drew, if we were to look at the spread of the data around the line, so here's the true line that we're trying to estimate, and we look at the data, the spread of the data around the line will be pretty uniform. It'll look like it's sort of in two constant bands, and we can get outliers very once in a while, but basically you can even eyeball these usually, and the spread won't look any different. And that's what homoscedasticity is, because everywhere within here, the distribution of the errors is identical. And the book has these drawn much better than I've drawn them. These are supposed to be normal distributions with peaks there with identical variances. Often, though, when you look at these data, when you look at economic data, what you'll see is they'll start off with a fairly nice distribution. But as you get further and further out here, the spread will get larger and larger. So you'll have lots of data. But you can see that down here they're fairly compact. But as you move further and further out in the x direction, you get a bigger spread of the data. So what's happening is, conditional on xi, you've got a really small variance. Conditional out here on xj, you've got a really big variance for the error terms. So in this case, sigma squared ui, the variance of the error term here, will not equal the variance out here. The variance of the error term here. The variance is getting bigger and bigger and bigger as x goes up. Now, it doesn't matter whether it could also start big and get small. It get small, look like a snake that just swallowed a mouse. It could be small at one end, have a big middle, and small at the other end. It doesn't matter. They could go up, down, up, down, up. It doesn't matter. All that matters is if they're the same or they're different across the x's. If they're different, then we have heteroscedasticity. This is the case of heteroscedasticity. If they're the same, then we have homoscedasticity. Now, heteroscedasticity arises quite naturally in a lot of economic applications. Suppose, for instance, we're running a regression yi is beta naught plus beta 1 xi plus ui. This is age, and this is earnings. So we want to know how earnings depend upon age. When you're young, your earnings are fairly small, and the variance of those earnings are fairly small. As you get older and older and older, your income tends to go up, and the variance of income tends to go up. So what you tend to see in this case is exactly what I just drew. You tend to see a much smaller variation in earnings at lower levels of age. This is age. But as you move out to higher and higher levels, higher and higher ages, the variance gets bigger and bigger as you move out because the variance in income is much larger. If this is sales for a store, say this is grocery store sales, and X is whatever X is. Well, the variance in sales for really small mom and pop firms is much, much smaller than the variance in sales for great big mega grocery stores. And so when you put all three of those things in the same sample, you tend to see heteroscedasticity because naturally the variance of the larger things is going to be much larger than the variance of the smaller things. The variance in income for the wealthy is much larger than the variance of income for the poor. Some wealthy people don't work at all, they have zero income. Some wealthy people work a huge amount and they have a huge income in addition to huge wealth. So there's huge variance in income for the very wealthy. The very poor have a much smaller variance in their income. They tend to mostly work because they have to, because they don't have wealth to live off of. And when they work, their incomes aren't that high. And so the variance in their incomes is much lower. And so in economics, when you just naturally see heteroscedasticity coming about. I guess in my notes, I use consumption is A plus B times disposable income for person I plus UI. This would likely be heteroscedastic because of this UI variance gives me a variance in C. The more this wiggles, the more this wiggles. Same things, the more this wiggles, the more this has to wiggle for a fixed here. So what you see then is that the variance in consumption for the poor, for low disposable incomes, is much smaller than the variance in consumption for the very wealthy. Some wealthy people don't spend that much money, wear old clothes, kind of proud of it sometimes. They drive crappy cars. Others spend tons and tons of money on consumption. There's a huge variance in consumption across the wealthy that's much larger than the variance for people with high incomes. That's much larger than the variance in consumption for people with lower incomes. So you just tend to see this often. So what are the implications of homoscedasticity? Up until now, we have not been assuming equal variances. We've been allowing we've been allowing for heteroscedasticity. We've been allowing for unequal variances. And so the formulas we've used for beta 1 hat, and particularly for the standard error of beta 1 hat, the formula for beta 1 hat just doesn't matter whether you have hetero or homoscedasticity, but the standard error of beta 1 hat and beta 0 hat are very different depending on whether you have homoscedasticity or heteroscedasticity. And as we'll see in a second, I forget what I was going to say. We'll see it in a second. Okay, so suppose we've been allowing for heteroscedasticity and all the results we've given so far for heteroscedasticity. What if we have homoscedasticity? Well, the estimators of beta 0 and beta 1 estimators, that's beta 1 hat, beta naught hat, beta 1 hat. Those are the estimators of beta naught, beta 1, remain unbiased and consistent. So it doesn't change the unbiased. We don't have to change the estimators. And they're still okay. So the estimators we've written down for beta 1 hat, like beta 1 hat, is the sum of the xi minus x bar, yi minus y bar, over the sum of the xi minus x bar squared. That's valid in both cases. It's unbiased and consistent in both of those cases. Okay, so it doesn't make any difference. Okay, the second thing is that the sampling distributions are still normal. So we can still use the normal approximations. But the formula for the standard errors of beta naught hat, beta 1 hat are different. They simplify. And I'll write this down in a second. I'll show you these different formulas. Finally, beta naught hat and beta 1 hat are still efficient. In fact, not only are they efficient, they are best. Under homoscedasticity, there is no other linear estimator that has a smaller variance. So let's look at this, that these standard errors are now different. That's the main change then, is that under homoscedasticity, we get a simplified formula for the standard errors. In this case, under homoscedasticity, sigma squared beta 1 hat just becomes sigma hat squared u hat over the sum from I equals 1 to n of the xi minus x bar squared. If you go back and look at our formula for beta 1 hat, the previous chapter that we wrote down, it was way more complicated than this. So this is a much simpler formula. The book writes this as s squared u hat. I like this better, but it doesn't make any difference. Those are exactly the same thing. And of course, the standard error of beta 1 hat is just the square root of sigma squared beta 1 hat. No hat. For beta 0 hat, the old formula was quite complicated. It had that H thing in it and a bunch of other stuff. We never actually wrote down what you'd use to estimate it. It's a lot simpler here. Sigma squared beta naught hat is just 1 over n times the sum from I equals 1 to n of the xi squareds times sigma hat squared u hat divided by the sum from I equals 1 to n of the xi minus x bar squared. And then the standard error of beta naught hat is just the square root of sigma squared beta naught hat. Nothing to it. All right, so that's that. So under homoscedasticity, two things change, three things. One, the formula for the standard error of beta 1 hat changes. Two, the standard error of beta naught hat changes. So the standard errors of the betas hats change. Secondly, not only is it efficient, but it's best. Now let me, just for fun and to make your life harder, that's not why. There's some value to doing this, and we'll see that later. Let me actually derive sigma squared beta 1 hat. Recall, beta 1 hat can be written beta 1 hat is beta 1 plus the sum of the xi minus x bar times ui over the sum of the xi minus x bar squared. We use this to show that it was unbiased. You took the expectation of beta 1 hat is beta 1 plus the expected value of this. And as long as those are uncorrelated, that has a 0 expectation. So the expected value of beta 1 hat is beta 1. So that's still the mean even under homoscedasticity. So what we want is the expected value of beta 1 hat minus beta 1 squared, conditional on xi, technically. Don't worry about that part too much. But this is the formula for the variance, right? It's always the expected value of xi minus the mean of x squared that's sigma squared x. That's how it's defined. So this is the expected value of it. That's the true mean. So we just take the estimate, say x, the estimate minus the true value squared an expectation, and that gives us. So this is, by definition, sigma squared beta 1 hat. So that's what we want to find. From here, beta 1 hat minus beta 1 is the sum of the xi minus x bar times mu I over the sum of the xi minus x bar, right? Just from there. So if I square it, I get that. And then I want to take the expected value. You may want to do that in 3 different lines. I don't know. Hit pause. Go ahead and write 3 separate lines if you like. So this is what we need to find this expectation in order to solve this. So let me just work with this last line here. That's equal to the expected value, and this part, of sum of the xi minus x bar times ui times the sum of the xi minus x bar times ui. That's just bringing the square inside. That's that squared divided by the sum of the xi minus x bar. This should have been squared. I forgot to put a square there. Squared. Now this part is where it gets a tiny bit tricky, but let's just see if we can work this out. Let me just write these out. This is just the top part. So I'm going to write out this sum and this sum. So what this, just the top line here, is going to be, the sum will be x1 minus x bar times u1 plus x2 minus x bar times u2 plus all the way out to xn minus x bar times un. That's just this part written out times the same thing, times here, x1 minus x bar times u1 plus x2 minus x bar times u2 plus xn minus x bar times un. Those things are n's. People get mad at my n's, sorry. remember, our sample size is n. So when I multiply this out, that's a 1. I'll get this times this plus this times this plus this times all up to here. Then I get this times this plus this times this plus this, and so on. I'll get this times this times this, times the next one, times the next one, all the way out to there. I'll get a ton of terms. And then I'm going to bring the expectation in. But what I want you to note is that the expected value of ui, uj, is equal to 0 when I does not equal j, because the ui's are independently and identically distributed. They're independent. They're not correlated. This is the correlation, I and j. We're making an assumption that our errors are uncorrelated. That's one of our 3 assumptions. It's actually the second one, that independence that we did. The implication of that is our errors are uncorrelated. So anytime I take a cross product, I'm gonna have an expectation of this, and then I'll have the person on the bottom. But anytime I bring the expectations operator through here, and the u's don't match, it's going to be 0. So the only terms that I'm going to end up caring about, everything will be 0, except when the u's match. So when I multiply this times this, that's non-zero. When I multiply this times this, that's non-zero, and so on. But everything else cancels out. So this is the same as the expected value of dropping all of the cross-product terms where the i's and j's don't match. This is the same as the expected value of the sum of the xi minus x bar squared times ui squared over the sum of the xi minus x bar squared squared. So I multiplied this out. I dropped all the terms where the ui's don't match, and you're left with that. Now I could bring the expectation, because these are independent, I could bring the expectation into here. So this is equal to, do I have room for it? Yeah. The sum of the xi minus x bar squared times the expected value of the ui squared divided by the sum of the xi minus x bar squared squared. Now, the next thing to note is that, the expected value of ui squared, that's the same as the expected value of ui minus 0 squared, is equal to sigma squared. We have the same variance for all I. If it was heteroscedasticity, this is sigma squared u, and I'd have to write an I here because it would differ depending upon which error we had. But since it's homoscedastic, those are all the same. That's what makes the formula different. The formula you had before had this, anyway, the formula before had an xi minus x bar up here, and that's because we couldn't make this assumption. But don't worry about what I just said. So this right here is going to be sigma squared u, because it's the same for all I. This is ui minus the mean of u. The mean of u is 0 by assumption 1. So this is just the variance right here. So this is equal to sigma squared times the sum of the xi minus x bar squared over the sum of the xi minus x bar squared squared. But these are the same, so it'll cancel. And so the variance sigma squared of beta 1 hat, the true variance, those cancel, is sigma squared u over the sum of the xi minus x bar squared, which is the formula that we had. To estimate, replace sigma squared u with s squared u. or what I call sigma squared hat u. So and that's the estimator that we wrote down initially. And so that's how you would find the variance for beta hat. To estimate this, you do that. And that works only when the errors are homoscedastic. Unfortunately, and it's really simple to work with that formula. Unfortunately, as I've been saying in economics, it's rare that you have homoscedasticity. So it's rare that you can use that formula with any confidence. And so what you do is you use the more general. So most of the time, almost always, generally, cannot assume homoscedasticity. That implies we can't use the simpler formula. So we use the one in the previous chapter instead, or earlier in this chapter. This is often called White's correction, after Hal White, who was an economist. He passed away not too long ago, but he was an economist at the University of California at San Diego, UCSD. And most of the computer packages, for historical reasons, still assume you have homoscedasticity. So most computer packages, remember I was saying they'll give you the coefficients, beta naught, beta 1. Most of the time, the computer package will give you the value, the estimate, the standard error, T and P value, the T-stat. This estimate is whatever it is. These standard errors usually assume homoscedasticity. And so instead, what you want to do is apply White's correction. And that allows for heteroscedasticity. And when I do the video on how to use eViews, and there may be more than one of those, I will show you which buttons to push to make sure that the computer packages does what's called White's correction. In 421, at least if I were teaching it, I've got some videos on YouTube which have the next class in the sequence if you want to watch those. But anyway, I would show you how to actually do White's correction through a series of regressions and what the computer is actually doing. But we don't need to worry about that for this class. So the point is that we do not want to assume homoscedasticity because it's rarely true. We want to assume heteroscedasticity. Unfortunately, the computer packages do assume that. And so we're going to have to push some special buttons to get the right standard errors to come out of these computer packages. And again, I will show you how to push the right buttons when the time comes. Okay, one last few things about this. And then we're done with this chapter. So if the three assumptions hold that we talked about earlier, and if the errors, the UIs, are homoscedastic, and that's a heroic assumption because they're often not, then the OLS estimators are unbiased, consistent, and best. And that means they have the smallest variance among all linear estimators. You can't find another estimator that has a smaller variance. So we say that the beta hats are blue. Best linear, unbiased estimator. And I've proved that a few times. The proof isn't too hard. We are not going to do it. This result comes from something called the Gauss-Markov theorem. The Gauss-Markov theorem. So it says, just what we just said, if the assumptions hold, so assumptions true, and homoscedastic, then the beta hats are blue. I often put it in capitals, best linear unbiased estimator. So if the three assumptions are true and you have homoscedasticity, then the beta hats are the best linear unbiased estimators. If any of the assumptions are violated, and as we've been saying, they often are, then that's no longer true. And that's what 421 is going to be all about. Okay, here's the Gauss-Markov theorem. What if the errors are correlated? What if this? What if that? Then what's our best estimator? How do we find the optimal estimator in those cases? And then you'll have some different formulas for beta 1 hat and beta 0 hat because they'll no longer be the best estimators. Sometimes they won't even be unbiased, depending upon how the assumptions are violated. If there's correlation between X and U, you're not even going to get unbiasedness. But there's a way you can use something called an instrumental variables estimator to get rid of that bias. And you'll learn about that in a later class. Last topic, and this is running a little long, sorry. Using t-statistics when the sample size is small. Remember that we're relying on the fact that the t-distribution that you talk so much about in statistics, that the t-distribution converges to a normal distribution. And as long as our sample size is, say, 100, earlier we said 30, it depends on the context. In regression models, let's say 100. As long as your sample size is bigger than 100, we don't need to worry about small sample issues. But what if your sample is smaller than a sample? So for small samples, you can use the t-distribution instead of the normal distribution if, one, all three assumptions hold. Two, the UIs are homoscedastic. And three, the regression errors are normal. You have to make a distributional assumption. We haven't done this up to this point. I've drawn them as though they're normal when I've been illustrating hetero and homoscedasticity, but we really haven't assumed the errors could be uniform, they could be anything. We just haven't made any assumption about what kind of distribution the errors are. But in this case, if we're going to use a t-distribution, rather than rely upon the large sample properties, the normal approximation, the law of large numbers, instead, if we're going to use small samples and t-statistics, then the regression errors have to be normal. Then you can use the t-test. That is the t-distribution. The t-statistic you use is the same as before. And so t is still beta hat minus beta 0 over the standard error of beta hat. Estimated minus hypothesized over the standard error of the estimate before, but you would use the t-distribution instead of normal, because you can't rely upon the normal approximation when the sample size is small. But in practice, in econ, it's rare that both 2, homoscedasticity, and 3, normal errors are true. And so if you don't have a large sample, if you don't have more than 100 observations, you're kind of in trouble. And there's ways to get around this that you would learn in grad school and other sorts of things. There's ways to sort of get through this problem. They're too hard for us. And so what we need to do is just make sure that our sample sizes are bigger than 100 so we can rely upon the normal approximation, or have darn good reason to believe our errors are normal and that we have homoscedasticity if we have a small sample so that we can actually use the t-distribution. But most of the time, you just don't want to use the t-distribution at all. Well, that's the end of this chapter, and we'll be back with chapter 6 soon. Thank you.